Good evening, everyone. So in our last video, we talked about how do we do the rotation of axis, and then if we project our original data in that rotated space, we could simplify our data, and then we were sort of in a position to identify some patterns that were sort of not possible to capture if we don't move from univariate way of analyzing to multivariate uh, analysis. So towards the end, we saw that we kind of projected our data in a orthogonal space where the original space and the rotated space are sort of related to each other through this relation. So in this video, what we are going to do, like how do we derive this rotation, right? How do we derive this rotation matrix? So in order to do this, what we are going to do, we take a simple uh, example, a 2D dimensional data set. And in that space is spanned over x and y. We have a vector at a distance r. And if I kind of try to go from Cartesian coordinate to polar coordinate, it's very simple to do. All you have to do is kind of find a relation, right? So if you have a circle going around of radius r, and then you try to find relation between x and r, so we know that this x and r are related through this relation. So x is nothing but the r cos theta, and this y is nothing but the r sine theta, right? So this is the base and this is the hypotenuse, and so it's very easy to find this relation. And likewise, they are related to each other, the y and r, through sine angle. So this is very easy. Now imagine if I rotate my vector, if I push it towards the y-axis by rotating it with angle phi, then what actually happens that you reach here, this r becomes here, and now there will be a new relationship between this x and r and y and r. So how do we derive that relation, right? So it's quite of very straightforward. So now our new x, it will be some fraction of x, let's say. So this x1 is is this one, r cos, and the angle now instead of theta becomes theta plus phi, so I write it down there. Likewise for y1 we have this relation, so instead of theta we have now sine theta plus phi. And so if I expand this identity, so now x1 becomes r cos theta cos phi minus r sine theta sine phi, and likewise y1 becomes r cos theta sine phi plus r sine theta cos phi. So it's a trigonometry relation, we all know this. And then if I plug these values that we had from the beginning, so then what will happen, this x1 is related to x through cos phi, right? And then you sort of substitute this r sine theta with y, so this becomes y sine phi. So this, likewise you can do it for y1. And if I write this in a matrix form, right? So if I take this x and y as a column vector and put it here, and then I write my new x values, x1 and y1. So you see, this is my new values, and this is my projection matrix, and this is my original values. So if I project this through on this space cos phi sine phi cos phi, you get a new x1 and y1. So you will be getting as many x1 and y1 as many phi's you can have. So for example, if you put cos phi, let's say you put phi equal to 45 degree, so then you get rotation matrix corresponding to that. You can put 60 degrees, so you will get a projection matrix corresponding to that. So this is a very simple and quite straightforward example, and this is what actually we will be doing in all our chemometrics, that we project our data from original space to to a projection matrix to derive the new x and y variables. So this is in a nutshell. I wanted to introduce this concept of rotation, which is very straightforward. It's not so complicated, but it's very useful. And now having understood the projection, rotation, then in coming video we will play with some numbers and then try to work with a fun data set, the wine data, the wine consumption habit of citizens living in different countries like USA, Russia, and then how their health conditions are correlated. So we will be taking that example and we will try to compute a lot of PCA statistics. How do we come to score matrix? How do we calculate the loading and all other statistics? So we will do with that fun data set, and um, we kind of document everything, how someone can compute the PCA and all its attributes just by using pen and paper. They don't have to use the computers. It's only needed because the data set is too large, not because the methods are complicated or the maths behind the principal component analysis is difficult. So that's my idea for the next lecture or the next video. But here I just wanted to introduce concept, how do we derive the rotation matrix. So this is very simple, right? So I hope you like and uh, kind of get an idea what is this rotation and how do we derive it. So all this stuff I try to cover here with a small example. Thank you. Have a nice day.